Very good afternoon, dear students. So today we are continuing with our previous topic, that is inverse Laplace transform, in this class on network analysis and synthesis. We had seen a few basic concepts regarding calculation of inverse Laplace transform, and we will continue with our discussion. So this is what we had discussed in previous class. I told you that partial fraction is a very important approach to obtain inverse Laplace transform, and we had seen that you can express the function of s as a rational number in the form of fractions as ps divided by qs, and the for partial fraction to be applicable, the degree of numerator must be less than the degree of denominator. Okay, and I had told you that our first step uh, before applying partial fraction approach is to check the degree, and second thing is to obtain the roots of the denominator, that is qs. Okay, and these roots we already know that these roots could be your distinct root, or you can say different roots. These roots could be repeated roots. These roots could be real or complex roots. So in the last class we had seen one example related to distinct roots as well as your roots were real. So today we will look into the cases where we will have instances of repeated roots and the complex roots. Okay, so that way today's class is very important, because we are going to deal some different kind of roots while calculating partial fraction for obtaining inverse Laplace transform. So this is what we had seen in the previous class. Your qs can be factorized into distinct and real roots like this. Then when we apply partial fraction approach, the function in s can be represented as a sum of a1 upon s plus p1 plus a2 upon s plus p2 and so on. So in a way what we have done, we have splitted our function in s as a sum of various fractions, sum of partial fractions in a way you can say. Okay, and once we represent our function in s like this, our only job which is left is to determine the value of these constants a1, a2 and your an. And once we are aware of these values, then we can directly apply our properties or the simple results of Laplace transform in order to obtain inverse Laplace transform. Okay, and this is how we determine the values of the constants. If we want to find out the value of a1, then what we will do, we will multiply uh, this fs with the corresponding factor, and we will substitute the value of that root. So here what we are doing, since we want to find out ak, we are multiplying fs with s plus pk, and whatever result we obtain, that result is you know, calculated by substituting the value of s equal to minus pk. Okay, so today we will start with another kind of roots, that is your repeated roots. So obviously if we have repeated roots, your expression will look like this. Ns is nothing but numerator, and in the denominator we have s minus p raised to power n. So n is the power. So obviously these roots are repeated. Okay, so now we want to expand this expression. So for that expression, it can be expanded like this. We represent our expression in the decreasing order of your powers like this. So things will be more clear when we take one example. So here we have s minus p raised to power n. So we are starting with s minus p raised to power n, then power is n minus 1, and then up to 1. Okay, so what we are doing, we are decreasing the value of exponent or the power of that particular root from the given value up to 1. So we keep on decreasing like that. Also notice the subscript which is associated with the constants that we are writing corresponding to these roots. So if we have n here, we are writing an. If we have n minus 1, this is an minus 1. If it is 1, we write a1. Okay, in different books you will find different kind of notation, but the procedure or the method is same everywhere. Okay, now how to find out the values of these ans, or an minus 1, or a1. So let us take an example that we have to find out the value of an minus 2. So if we need to find out this an minus 2, then this is how we will obtain. So what we will do, we will write 1 by 2 factorial. So this is n minus 2, that's why we have 2 factorial. Then d by ds, we are differentiating with respect to s. So since we are considering n minus 2 here, so that's why it is second order differentiation. Okay, and this is the same kind of thing. This was the given function in s. We are multiplying this function in s by the highest power of the root, that is s minus p raised to power n, and we are substituting the value of root as s equal to p. So had it been s plus p raised to power n, we would have substituted s equal to minus p. Now here our root is s minus p raised to power n. That's why we are substituting s equal to p. Okay. So this thing you have to take care of while finding out the value of the repeated roots. So if we generalize this, like we won't need to find out the value of a n minus k, in that case it will be 1 by k factorial, then kth order differentiation with respect to s. This will remain same for every constant. Okay, and you are substituting s is equal to p. I hope this thing is clear, and it will be more clear as we see one example related to this in the next slide. Okay, so let us see that. This is the example. So we need to find out the inverse Laplace transform of the function, this one. I told you before we calculate any inverse Laplace transform using partial fraction approach, we first need to check whether the degree of numerator is less than the degree of denominator or not. So here we see that the degree of numerator is 0, s raised to power 0, and in numerator degree of s is 3. Okay, so we can directly apply partial fraction approach. So before we move further, we need to find out the factors which are there for your denominator polynomial. So if you look at this thing carefully, if you factorize, these are the three factors you are going to get, that is s into s plus 6 into s plus 6, or in a way you have s into s plus 6 raised to power 2. Okay, so what you have one root, that is s, and you have two repeated roots, that is s equal to minus 6. Okay, so calculation of s we have already seen, which is a distinct root and real root. Now we need to see the calculation of your repeated roots. So as we discussed in the previous slide, what we need to do, we need to split our given function s as sum of different, you can say, partial fractions. Okay, so we start with the highest power, that is s plus 6 raised to power 2. Then we move to next power, that is s plus 6 raised to power 1. I told you we will start with the highest power and we will keep on decreasing our power and move up to when our power becomes 1. So this has s plus 6 raised to power 1, and their corresponding constants are a1 and a2. Is that okay? And this is the third term which is associated with third factor. Constant assumed is a3 and the term is a3 by s. So now our job is to find out a1, a2 and a3. Now let us see how to find out the value of a1. So again, have a look at the previous slide. So here you see, if you want to find out the term an minus k, means the constant associated with kth power, then you need to have 1 by k factorial dk by dsk, means kth order differentiation. So same is the case here. We need to find out the value of a1, means a1 is associated with the highest power, that is 2. Okay, so what we will do here, see here, for a1, let me correlate it like this. So here in the previous slide we had written a n minus k. This is what we had written. Okay, and there we had 1 by k factorial like this. Fine. So here, now you see, this is what we need to apply here. So if you look at here, what we are doing, we are multiplying our given function with the power, highest power, that is s plus 6 raised to power 2. This you have to do for every function. Okay, this is to be done for every function. Fine. So now what is the value of k here? So since we are taking the highest power, the value of k will be your nothing but n, because value of the k is 2, which is nothing but n, and n minus k will be 0. Okay, so this, if your k is n, so it will become a0. So that's why there is no differentiation. See, 1 by 0 factorial, that is 1, d0 by ds0, this is also 1. So it means if you want to find out the first one, that is this a1, you don't require any differentiation. So you have to, s plus 6 will be cancelled with this. Okay, 2 by s, you put s equal to minus 6, and this is your a1. Okay, next we need to find out this one, this a2. So here, what is the value of k? The value of k is 1. Okay, so if this is 1, so you see here, 1 by 1 factorial, that is 1, and this is d by ds. Okay, so see, you have d by ds. This is nothing but your given function is multiplied, always multiplied with the highest power, that is s plus 6 ki power 2. Okay, so you have to, this will be cancelled. You have 2 by s, and you have to differentiate 2 by s. So differentiation of 2 by s will become minus 2 by s square, and you need to substitute s equal to minus 6. So you come out, your value comes out to be a2 is equal to minus 1 by 18. Okay, so students, here it is using the you can say subscript 1 and 2, which is creating a bit confusion. Okay, so what I'll do, you should represent it like this. The highest power, for highest power, you take that constant at a0. I will advise you this thing. Then the next you take as 1. Next you take as a2. Okay, means you keep on decreasing the powers in the denominator, and in the numerator you start with 0, a0, a1, and like this. Okay, so by looking at 0, you will immediately remember that k is 0, here k is 1, here k is 2, like that. So instead of using this a1, a2, you try to use here at a0 and a1. This will create less confusion while calculating this. Okay, and then this you can take either as a3, or you can also take this as b, just to differentiate it from repeated roots. Okay, so now we need to find out a3. So we already know that how to obtain a3. It is a distinct and real root. So the given function is this one. So this need to be multiplied with s. So we have multiplied with s here. Then the value of the root is s equal to 0. So s will be cancelled. If you put s equal to 0, it will be a3 will be 1 by 18. Okay, so what we get here, we substitute the values of a1, a2, and a3 here. So this is what we get. Okay, So if we move further, so this is, you can compute directly. So now you see here, this is minus 1 by 3 s plus 6 raised to power 2. Okay, so if you recall your properties of Laplace transform, this is s square. So what is the inverse Laplace of 1 by s square? The inverse Laplace of 1 by s square is what? T. Fine. So here what we have, s plus 6 means there is frequency shifting. Okay, so minus 1 by 3 is a constant. So for the first term, your inverse Laplace will be minus 1 by 3. Okay, then t, then frequency shifting implies that you have e raised to power minus 60 term multiplied with it. So this is the inverse Laplace transform of the first term. Okay, how about the second term? If you look at this thing carefully, the inverse Laplace of 1 by s, this is what? You already know that the inverse Laplace of this is ut. Okay, and we have s plus 6 means there is frequency shifting, and the constant is minus 1 by 18. So inverse Laplace of this will be minus 1 by 18. Okay, then you have e raised to power minus 60 into ut. Okay, so this is the inverse Laplace of your second term. And how about the third term? Third term is just 1 by 18 divided by s. So it will be straightforward, there is no shifting here. It will be straightforward 1 by 18 ut, and then you can add them together. Okay, so this is one term, this is another term, this is third term. If you add them together, you will get the final inverse Laplace transform of the given function. Okay, so I hope with this example you are very clear of obtaining the inverse Laplace transform using partial fraction for repeated roots. Okay. So, dear students, after having a look at the calculation with regard to repeated roots using partial fraction approach, now we need to find out a few inverse Laplace transforms so that we are able to further reinforce our concepts of inverse Laplace transforms. So, these are very simple questions. I will advise you that you also work out simultaneously, and I'll also explain how to solve these inverse Laplace transform so that you get a complete idea of the things with regard to your inverse Laplace transform. And this practice is very important. If you are very comfortable with the calculation of Laplace transform and inverse Laplace transform, then solving numericals using this when we will have circuit elements in our calculation, it will be very easy. So just have a look at this. The first question is 8 by s into s plus 2. Okay, so the power of numerator is less than denominator. First condition satisfied. Now second is we have to see the uh, we have to see the roots of this uh, numerical. Okay, there are two roots, s equal to 0 and minus 2, and these roots are your distinct and real roots. So obviously we will express this as partial fraction. So it will be, you can say, a by s. Okay, then plus we'll write b by s plus 2. So this is what we had seen with respect to distinct roots. We have expressed this function as sum of two partial fraction. Now we need to find out the value of a and b. And how do we do that? So first you suppress s. Okay, suppressing s means I told you that we need to multiply this function with s. So if you do multiply with s, s and s will be cancelled. So indirectly we are suppressing s. So for calculating the value of a for s, you suppress s here and put value of that root, that is s equal to 0. If you put s equal to 0, it will be 8 by 2. Okay, so your a will be, how do you find out a? You multiply s with 8 by s into s plus 2. Okay, so this s and s will be cancelled. You have 8 by s plus 2. You have to substitute the value of s equal to 0. If you do that, s is 0, 8 by 2 is 4. So the value of a comes out to be 4. Fine. Now we need to find out the value of b. So for value of b, we have to suppress now what? S plus 2. So we'll be left with s here, 8 by s, and you have to substitute the value of s equal to minus 2. So if you put s equal to minus 2 here, the value of b will be 8 by minus 2, that is your minus 4. So what we have, a equal to 4, b equal to minus 4, and we have to substitute in this expression. Then you can directly take inverse Laplace. What you have, 4 by s. So 4 by s is nothing but inverse Laplace will be 4 ut. Okay, then b is minus 4, so we have minus 4, 1 by s plus 2. S plus 2 is nothing but frequency shifting, so e raised to power minus 2t. This is your frequency shifting, and since it is 1 by s, so it will be ut, and you can take ut as common, and this is the inverse Laplace transform of 8 by s into s plus 2. So this is how by applying partial fraction we are able to split our s domain function into simple partial fractions where we can directly apply our inverse Laplace transform results. Okay, so now let us discuss second example. Okay, so here what we have, 8 into s plus 1 divided by s into s plus 2. So first thing that we check is degree of numerator is less than degree of denominator. Okay, second thing we check is the roots. Roots are already given. There are two roots, one is 0 and another is minus 2. These roots are real and distinct. Okay, so we express this as sum of different fractions, which will be nothing but a by s, okay, then plus b by s minus 2. So this is nothing but exactly same way we proceeded in the previous numerical. So all that will be there is there will be change in the value of a and b when you substitute the values of uh, the roots. Okay, so in order to find out the value of a, you need to suppress s. You suppress s, put s equal to 0. So this is 0, this is 0, 8 by 2, that means you get 4. Okay, so it will be 4 by s plus. Now we need to find out value b. You need to suppress s plus 2. So you are left with this 8 into s plus 1 divided by s. You have to substitute s equal to minus 2. So what you will have, 8, okay, you have s plus 1, so it is minus 2 plus 1. Okay, then divide by s. S is also minus 2. This is the value of b, and on the whole you have s plus 2. Okay, and this thing, it comes out to be what? It comes out to be, sorry, minus 2 plus 1. So this comes out to be plus 4. Okay, so a is also 4, b is also 4. Rest of the result is same. You'll get 4 ut plus 4 e raised to minus 2t into ut. So this will be the direct answer for your second numerical. Very, very simple. Once you are comfortable with the application of properties and simple results, it is just a child's job to find out inverse Laplace transform of a given function. Okay, so now we see example number 3. So here again we see the degree of numerator is less than degree of denominator. Now here if we look at the roots, we have s square. Okay, in the denominator we have s square into s plus 2. So what does it mean? We have one distinct root and real root, another is this is repeated root. Okay, so for this in the numerator we have 8 into s plus 1. Okay, so here we will express this as a sum of the fractions that we discussed. So first let us start with repeated one. I told you we take s square here. So for s square, that is highest power, we take a0. Okay, after that we take the next down the line, that is after s square become s1 and a0 becomes a1. So at s1 we stop. Then plus we have another root, that is s plus 2. So for that we write say b. Okay, b by s plus 2. Very simple. Now we need to find out the value of a naught. So for finding out a naught, if you remember, for a naught there will be no differentiation and we will have 0 factorial, that is 1. So we have to simply multiply this with s square, and for that this s square will be cancelled. Okay, so the value of s is 0. Okay, so for a naught it will come out to be, here s square cancelled, you'll be left with this one, and you substitute s equal to 0. So 0 means this s0, this s0, 8 into 1 by 2. So you get a naught as 4. Very simple. Okay, now we need to find out a1. So how will you find out a1? So this is 1, means 1 by 1 factorial. So 1 by 1 factorial is nothing but 1. Okay, then we have first order differentiation, that is d by ds. Okay, d by ds of what? D by ds of this function multiplied with s square, highest power. So if you do that, this s square will be cancelled. Okay, so means you have to differentiate this, 8 into s plus 1 divided by s plus 2. You know the rules of differentiation when we have uh, s as a form of fraction. So it will be s plus 2 square. Okay, I think I need not explain it further. So if you differentiate s plus 1 by s plus 2, it will be, 8 is a constant, it will remain as it is. So this will be the answer that you will be getting, 8 by s plus 2 square. This is what you will get if you differentiate. If you differentiate this. Okay, so here now you have to substitute what, since you are calculating for s square, so you'll put the value of s as 0. Okay, so if you put 0, it will be 2 square 4, 8 by 4. A1 is, what do you get? You get a1 as 2. Okay, and now we need to find out b. So in order to find out b, its factor or its root is you can say s plus 2. Here you have to suppress s plus 2. You'll be left with 8 into s plus 1 by s square. Okay, so and you have to substitute s equal to minus 2. So for b, what will you get? You will get 8 into s is minus 2 plus 1. Okay, this is suppressed. You have s square and s is minus 2. Minus 2 square is nothing but 4. Okay, 4. So if you do that, the value of b comes out to be minus 2. Minus 2. Okay, so we have a naught as 4. We have a1 as 2. Okay, and we have b as -2. So these are the simple terms. So if you apply inverse Laplace, a naught by s square, a naught is 4, s square is inverse, its Laplace inverse is t. So what do you have? You have 4t. Fine. Then for this term, a1 is what? A1 is 2. So you'll have plus 2 ut. Okay. Ut is implied here also along with t. So I have not written it. Fine. So 4t ut plus 2 ut. Then for b we have -2. So it will be -2. Okay. Frequency shifting is there. That means e raised to power -2t. And 1 by s is there. So it means ut. So the final answer will be 4t ut plus 2 ut minus 2 e raised by -2t plus ut. So this is the inverse Laplace of this function. That is your third question. Okay, I hope all things are clear, and you see just by having small awareness regarding properties and your partial fraction approach, you can very easily calculate inverse Laplace transform. Okay, so our next numerical is D. So there is a small difference in the numerical that we just discussed, that is numerical C and D. Here you see in the previous numerical it was s square, here we have s plus 2 square. So we have changed our repeated roots. Rest of the question is same. So instead of discussing it completely, I'll just write the partial fractions. I'll tell you the value of a0, a1, a2, and then I'll tell you the answer. Then you can solve that numerical at your home, and in case of any confusion you can discuss that thing later on. Okay, so if we carefully observe this, we have a repeated root, that is s plus 2 whole square. We have a distinct root, that is s. So we can represent this thing as a sum of partial fractions. So let us start with s plus 2 square. So we will write s plus 2 whole square. Okay, and I told you that with the highest power you take your constant as a0. Fine. Then we move to next power in the decreasing order, and that will be s plus 2 raised to power 1. Okay, then its constant we will take as a1. Okay, plus then we have a distinct root. For that we will take our constant as b. So it will be b by s. So I think all the things are very clear. So if you need to find out a naught, so there is no differentiation. Factorial, 0 factorial is also 1. You will multiply this term with s plus 2 square, and you will substitute s equal to -2, and you will get the value of a naught as 4. Okay, then what you will do, you will find out a1. For this you will have 1 factorial, which is again 1, but you will require first order differentiation. So for first order differentiation, you will again multiply this term with s plus 2 whole square. You will be left with 8 into s plus 1 by s. You will differentiate it with respect to s and substitute the value of s equal to -2. And for that, you will get the value of a1 equals to -2. Okay, and in order to find out b, which is a distinct root, you will suppress s. Okay, so after you suppress s, you will put the value of s equal to 0 in the remaining term. So this is 0. You'll have 8 by 4, that is nothing but it is your 2. So value of b will come out to be 2. So these are the 3 constants. So once you have these 3 constants, you can take easily inverse Laplace of this. So you see here, this is s square, means you have ramp function. but s plus 2, it implies frequency shifting. So a naught is 4, then you will have t. Frequency shifting means e raised to power minus 2t. Okay, ut is implied here. This is inverse Laplace of first term. Then let us come to second term. A1 is minus 2, so you will have minus 2. You have frequency shifting, that is e raised to power minus 2t. Okay, then you have simply 1 by s, that means it is ut. Okay, then your third term, the value of b is 2, so you will have 2, and you have s, that is simply ut. So this is the answer for your question number D. Okay, I hope everything is pretty clear to all of you. Fine. So with this, dear students, we are complete with the discussion related to calculation of inverse Laplace transform for two kind of roots. One is your distinct and real roots, and second is your real and repeated roots. Okay, now one kind of roots we are left with, and those roots are called as complex roots. And wherever we obviously in the name itself it is there that those are complex roots, so obviously there seems to be some complexity in the solution of those roots using partial fraction. So that's why we need to take that thing in bit detail. So our next question, that is question number E, it has complex roots in it. So we will now solve this numerical. And let me tell you, dear students, even if you do not assume that these are complex roots, still by using the concepts we have already developed for your distinct roots and repeated roots, those concepts can be applied here, but that will be a bit lengthy process. I'll explain both the things to you so that you are able to appreciate that by applying method related to complex you can solve it, and even without that also you can solve the given numerical. So in fact, I have worked out solution of this numerical with my own hand, and I have put that solution in the slide, in the coming slide, so that we are able to discuss it in effective manner. So let us move to next slide, and we will discuss this question E. Okay, this is the question. So we have to obtain the inverse Laplace of 12s divided by s square plus 4s plus 8. So as I told you, first thing that we need to look into is the degree of numerator should be less than degree of denominator. It is already there. Next thing is we need to find out the roots of this. This is a quadratic equation. So we need to solve the quadratic equation, and we know that for a quadratic equation the two roots are defined like this: minus b plus minus under the root b square minus 4ac upon 2a. And if we substitute the value of a, b and c respectively, this is what we get. And you notice one thing here, that in the under the root you have a negative value. So if we have negative value under the root, we will have a complex value associated with it. Okay, so if you solve this, the two roots that you come across is this one, that is minus 2 plus minus 2j. So here what we have come across, the two roots of this polynomial in S as denominator, these come out to be your complex roots. Okay, so students, though I am saying these are complex roots, but on the other hand side, if you forget whether these are real or complex, but these two roots are distinct roots. Okay, so if you assume these roots as distinct roots, so same method can be used that we have applied for distinct roots. So first I'll apply that method of distinct roots here and come at the solution. And then I will specifically apply the method of complex roots, which is a small shortcut method, and we will come at the same solution. Try to understand that. So here, these are the two roots. I have expressed this quadratic equation in the form of its factors like this. This is pretty clear. These are the values of roots and you can express it like this. And as we did in distinct roots, we have split our given expression as sum of partial fraction. This is one root, this is another root. Okay, the only difference is earlier what we were doing, we were writing it as a1, a2 or a or b, but here we have written a1 and a1 star. And why are we writing a1 star? Because if you look at these two roots carefully, the only difference is these two roots are complex conjugate of each other. Okay, so even if you take this a1 as a and a1 star as b, you will find that b is equal to complex conjugate of a1. So that's why like even if you do not assume it as complex conjugate and you solve, you will find this value as complex conjugate only. So just to shortcut the calculation, I have taken this as complex conjugate. So that's why we need to find out a1 only. So once we have obtained a1, we know that the second constant is going to be simply complex conjugate of that. Okay, so this is what we had written for our distinct roots earlier also. So same thing up to this point. There is nothing new except one point, that the second constant will be complex conjugate of the first constant. Okay, next. So this is what we have obtained in the previous slide. Now, as I told you, we need to find out the value of a1. So in order to find out the value of a1, what we need to do? We need to suppress the factor of a1. Okay, just go back. See here in this one. This is the, we need to multiply this expression, this complete expression, with the factor of a1. Okay, so it means this will be suppressed or this will be cancelled. So we will be left with 12 into s by s plus 2 minus 2j. So here in this one, we have to substitute s is equal to minus 2 minus 2j. Okay, let us see that. So this is what we have done. Okay, see 12s, we are now not considering 12, we are taking 12 is a constant, s upon s plus 2 minus 2j. So this is what we have substituted, s equals to minus 2 minus 2j. Okay, then what we had this one, s plus 2 minus 2j. So s plus 2, so this is s plus 2 minus 2j, and what we have substituted for s, minus 2 minus 2j. So what we have done, we have substituted the value of s here. Okay, and if we solve it, this is what we get for a1. Very simple. So after we have got the value of a1, then what will be a1 star? It will be complex conjugate of this. So this is a1 star. So that's why I have taken second constant as a1 star. Otherwise, you could calculate in the same way as you have done it. So students, that's why we have not calculated a1 star. You could do that thing also. Okay, so once we have obtained value of a1 and a1 star, okay, then we have to obtain the inverse Laplace of that. Okay, so we have to obtain inverse Laplace like this. We have substituted the value of a1 and a1 star here. See, we have substituted the value of a1 and a1 star. Okay, and then these are complex numbers. So let us solve this. So what we have done here, we have opened this bracket. We have got this one. If you open this bracket, you will get this one. Okay, so if you move forward, we will take this thing as common from all the terms, and we will be left with this e raised to power minus 2j t minus j, like this. Okay, and you all know that what is the meaning of e raised to power j theta. Okay, e raised to power j theta is nothing but cos theta plus j sin theta. So by substituting this value, we get this one. So e raised to minus 2jt is nothing but cos 2t minus j sine 2t. So for this minus j outside, you put cos 2t minus j sine 2t. Similarly, this one. So this is very simple mathematics. You all are second year students, very easily can solve that. So if you solve further, you will get these terms. And if you carefully see, this is cos 2t, cos 2t, these are added together. This is minus sine 2t, minus sine 2t, these are added together. And these terms will be cancelled. See, minus j sine 2t plus j sine 2t, minus j cos 2t plus j cos 2t. Okay. So these will be cancelled and you are left with simply this one, 1 by 2 e raised by minus 2t, 2 cos 2t minus 2 sine 2t. Okay. So we have got this solution. And if we move forward, this 2 is common, that will come out and 1 by 2 will be cancelled, and we get this result. Okay. Now if you remember, I had left 12 earlier, so we need to now multiply with 12. So this is the answer. This is the inverse Laplace transform of the expression or the numerical that we had seen, that is this one. So inverse Laplace of this is this one, 12 e raised by minus 2t multiplied cos 2t minus sine 2t. Okay. And you all are expert of trigonometric expressions. So if you apply these expressions, you can write a concise expression for this. This cos 2t and sine 2t, they can be combined in the form of cos here. So I leave it to you to find out this answer. So you get 12 under root 2 e raised by minus 2t cos 2t plus 45. Okay. Here the concept of cos a plus b, that is cos a cos b minus sin a sin b, those trigonometric identities are being used. Okay. Otherwise, if you leave it here also, it is okay, but you need to look into the solution of this also. So students, here our roots were complex, and without using any other thing except that the two roots are complex conjugate, we are able to arrive at the solution. Okay. So I stop here. And we will continue in the next class. And in next class, this inverse Laplace will be over, and we will discuss the concept of Laplace transform for circuit analysis in the next class. So I again advise you to practice more and more for calculation regarding Laplace and inverse Laplace, so that you become comfortable with the solution of Laplace transform. Okay. Thank you. Thank you very much.